Start recording. Start the virtual camera. Share my screen. Cancel this. Turn on my camera. Okay. Alright, so let's go ahead and start the office hours. Can you hear me on Discord?
Yes, I can.
Okay. I can't hear you because I accidentally have my speaker muted. Go and talk one more time.
Hello?
Okay, cool, we're good. My computer's charged today, so it shouldn't be laggy in the call or in the video if you guys look at it afterwards. But we can go ahead and start on. I think you guys said homework 7 isn't due until Friday.
Tomorrow, yeah.
Okay, so then we're continuing with that, and we left off on some of the system Verilog questions. Is that right?
I couldn't make it yesterday. I was
Oh,
trying to head
yes,
home
that's right. That's
before
right.
that storm. That never happened.
Yeah. Let me think. Oh yes, so where we left off yesterday was with some of the system Verilog questions, but I can start with wherever you guys want. So if you have any particular questions you want to talk about, we can go over those. Because otherwise, I'm just going to start babbling on. so give me something to work with. We can move. It's fine. You sure? Okay. What about on Discord? Do you have any homework recommendation or question recommendations that you want to go over, or you're just here for the ride?
Oh, I'm just here for the ride, yeah.
Okay. Okay. So I'll tell you what. I'll open up the homework and I'll take a look at what we got, and I'll see what I can talk about. Assignments. Okay, I guess probably what we'd wanna do is the FSM question for System Verilog, because I don't think I've gone over that yet with anyone. Yes. I think what I'll do though is I'll do a different FSM than the one that's on the homework. So the one they have on the homework is it. Actually, I'll ask you guys, what kind of FSM is it? Is it more or melee on the homework? Should be question 3G.
It's some more FSM?
Okay, so one thinks it's a more. I'll wait till.
Can I see it?
Yeah, sure.
Okay. That is let's see, our inputs. Wait, our outputs are A and B and our inputs. So that is a more because we don't have like the input-output between.
Yes, you're both right.
States.
Yeah.
Okay.
If this was a melee FSM, you'd have the output asserting on a transition, but here we have the outputs asserting within those states. So this is a more FSM. Okay, so I'll go ahead and do one with. Yeah, I'll just draw up a diagram up on the board with 5 states, just some different interconnections. Move this. There we go. And I'll have it use 2 inputs and 2 outputs. Okay, I've gone ahead and drawn in another 5-state more FSM. I'm going to go ahead and write my outputs within the states as well. Okay, just as a quick side note, we have 2 input bits, A bit 1 and A bit 0, and then we have 2 output bits, Y bit 1 and Y bit 0. All I've done is I've drawn 5 states with interconnections which depend on the inputs A1 and A0, and in each state I've written what the value of Y is for both bits of Y. You'll also notice that I've used a little bit of non-formal notation, particularly here on state 3. All that I intend for this, and this is something you can draw in on your schematics, because you can translate this to code pretty easily. That's why I'm doing this. But what I mean by this is, when you're in state 3 and you receive both bits are on, then you go to state 4. But in any other case, you remain in state 3. That's what I mean by this. And you can write it in a Boolean equation, and I'll write that out. Actually, no, I won't write it out. I'll ask you guys, how would I say else here? How could you write out else?
So that would be. I think it would just be not A1, A0.
Yes, exactly. And you could also write this as doing De Morgan's theorem. So not A1 or not A0. Now when I say else, we can code that up pretty easily, but this is what we mean in terms of hardware. Okay.
And then what's the transition between S1 and S2? So not A bar or A1, so it would have to be A1.
This transition here?
Yeah.
So I specifically put nothing on this transition. What does that mean?
Oh, so that means it just there's so it just goes there.
Yeah. So you'll notice there are no other transitions coming out of S1.
Yeah.
This is the only one.
Oh. I see.
So you always take this transition,
Okay.
essentially. That's what that means. Okay, any other questions about the rest of my diagram? You'll notice I actually did that exact same thing for this transition here back to the reset. And it's fine if you don't get down every specific detail for this FSM. The point of this is just learning how to get FSM into System Verilog code. I don't really care that you get the example perfectly down. I care that you know how to turn this into System Verilog. Okay. Same thing as always, I'm going to go ahead and open up a text document so I can start typing in the System Verilog code for that FSM behind me.
Did you record yesterday's session?
Yes, I uploaded it earlier today.
Awesome.
Yes. Okay, cool. So I have the code up on Discord, or rather an image with my System Verilog code up on Discord. So if you want, you can either scoot over next to me to look at it, or you can go on Discord.
I just don't want the feedback
Yeah.
to happen, so hopefully I can turn it off.
Yeah, I can show you how to mute it.
Okay.
Actually, I'll just use this one because that one's an SV file. Okay, module. Whatever, it doesn't matter. I can type it up. I just wanted to get nice highlighting for the syntax, but it doesn't really matter. So I'll go ahead and call this module FSM example. Again, it doesn't really matter what you name your module. The most important part is that you understand the purpose of the module and you name it such that you understand its purpose. Now the next thing for any module that we're going to put in is we have to put in our port list. So the port list always goes within the parentheses starting after your module name. I mentioned a little bit last time that if you have a parameterized module, I'll talk about what that is later if anyone is curious. Parameterizations go right before the port list. It's nudged in between there. Doesn't matter if there's spaces, that's just formatting. Okay, so remember what we put in our port list is all the things coming in and out of our circuit. So what are the things that are coming into our circuit and what are the things that are coming out of our circuit?
So we have to do the input with logic 1 to 0. Input A.
Yeah, so input A is something I'm going to have to type up there. That's right. There we go. Okay, yeah, so I'll go ahead and write that in. So we have input, and then I don't just type input, I type input
Logic 1.
Input logic, and then I type my bit width 1 to 0 because it's 2 bits. Okay, and then I'll call this A. And what do I have now? Or what else do I need to put in? And I guess I'll do this on a new line. So what's the other thing I have to put in here? Well, I'll give everyone a hint. I'll type in output.
Logic.
Yeah. Output logic, same bit width, and specifically on the board, might be a little hard to see, but my outputs are
Oh,
called
by the
a Y.
way, this is what it looks like.
Yeah.
Yeah. It's just covering it.
Oh, is it? Okay.
And
I will move that a little more.
just there you go. Now we can see it. Thank you.
Go ahead and make a mental note of that. Okay, cool. So I went ahead and typed it up. So I have my inputs A and my outputs Y, and now I can actually design the inner workings of my module. And so for FSMs, typically you start with state names on your transition diagram, and then when you do it by hand, you give them encodings. So instead of names for your states, you have actual bits that correspond to those states. You do the same thing in code, but there are easier and harder ways of doing it. The hard way is literally using the bit string, the string of bits, and using that for those states. That's really hard to do because you need to remember in your head what those bits represent in terms of your state names. So instead, you can do what's called, you can use what are called parameters, which allow you to use names to represent bits. So I'll go ahead and type up an example. I'll call this SR. And I guess we'll decide now what kind of state encodings do we want to use. Do we want to use one hot or binary? I don't really care. Okay, let's do binary. So we have 5 states. How many bits do we need to represent 5 states with binary encoding? Yeah, we're going to need 3 bits. That's right. So I'll go ahead and type up them. So whenever I have to specify multiple bits, I have to put how many bits are occurring in my signal, followed by an apostrophe. And then the next thing that comes is the format I'm going to be writing my number in. I can put B for I'm going to write it in binary. I can put D for I'm writing it in decimal. I can put H for writing it in hexadecimal.
Can you actually, because I had problems with this during the lab, can you just do one hexadecimal example?
Sure, yeah. So
Can you do HO? I can't remember what I was having problems with.
So something like this would be valid. 3 bits of hex 7. 7 is a hexadecimal number. And specifically in binary, this would be represented as 111.
Okay, and you could do like H capital A. I think
yes.
that's what was like throwing us off.
But you need to change this bit width. Because A in binary is what?
Oh, well, A is 10. So,
And that's how you'd say, and that's how you would say 10 in binary, right?
okay.
But how many bits do I need to write that out?
4, I see.
And so that's why I got to change this number here. That number at the beginning is independent. It doesn't matter what you put here. It is completely unrelated. This tells you how many binary bits you're going to be using, because everything's in binary. So even if I put decimal over here, I'm not getting 4 decimal digits. I'm getting 4 bits, binary bits. So the maximum decimal number I could put here would be 15. I can't go any higher.
Yeah.
So just keep that in mind. This number of the number of bits you're using and the format that you're typing it out in have nothing in common.
Okay.
That's a very fine point that a lot of students miss out on. For this, though, like I mentioned, we're doing 3 bits. And just to be different, I will do it in decimal. So I'll say this first one is decimal 0. And I'll go ahead and do the rest of the states as well. So I have state SR, S1, S2, S3, and S4. And I'll label them decimal 1, 2, 3, and 4. Now I've written them out in the code in decimal, but keep in mind that the way this is encoded in the actual hardware is in binary, which would look like this in my comments. And what's the last one? 100. So that's what the actual binary encodings are. Okay. Any questions so far? All right. So now that I have these, all this is doing is it's saying if I ever want to use 3 bits of binary 0, I can just say SR in my code, and it's going to understand that as 3 bits of binary 0. Same thing for S1, it's going to understand it as 3 bits of binary 1. S2 is going to be 3 bits of binary 2, etc. There's another way you can do this, which is via enumeration. You'll learn about that in class. She has examples. So I'm showing you a different way to do it, so that you have multiple ways to do it if you ever forget one. Okay, so
This is just kind of like making it a variable?
yeah. Yeah, you can think of it like encoding if you need a constant. These are constants. Yeah. Though in hardware, these don't exist. These are just abstract things for us to type up. In hardware, it's literally 3 wires that have ground on them, versus or 2 wires that have ground and one that has VDD on it. So this is just for us to be able to type less and to understand better. Okay.
So, just a quick question.
Yep.
So this would be like hashtag define in C, right?
Yep, exactly. Something like that, for example. Yep, it's exactly the same.
Okay, thank you.
Okay. This is non-synthesizable code. Like I just said, that's not what you see on the hardware. You see the actual wires, so just keep that in mind. Now we can go ahead and continue with the actual work. So there are a few things we need to do for our FSM. I'm going to start with the first thing, which is, remember in your schematic, you're going to have a register that holds all your states. That's typically called the state register for hopefully obvious reasons. I'm spelling that wrong. Register. And this register is just a flip-flop, like you guys have been using for the entire semester. But the only difference is that it's a multi-bit register, which is to say there are multiple flip-flops in a row that all have the same clock, but with different inputs feeding into them. And so the way you make a flip-flop, if you don't recall in System Verilog, is you use an always block underscore FF. That FF just stands for flip-flop. And then you begin this @ sign, and then here you have a set of parentheses. So the way that I kind of read this to myself is, this is a flip-flop, and at whatever is in its parentheses, I'm going to reevaluate the inside block. So those parentheses are what's called the sensitivity list. And whatever I put in here, say it's pos edge clock, what this is going to do is every time you have a positive edge of your clock signal, it's going to go inside whatever I type inside of this block, and it's going to reevaluate it. So exactly as how we expect a flip-flop to behave. On the rising edge of a clock, it reads in the value. And so that's what we're going to have happen. So what I'm going to put in here is if, oh, and I forgot something. See if you guys can figure out what input signal I forgot.
Oh, reset?
That's one of them. There are two that I forgot.
The reset for state reset, right?
Yep, reset. So reset's one of them. What's the other
Do
one?
you need to specify that when you have your flip-flop? I thought that was always kind of like defaulting.
Yeah, by default,
state
in schematics, yeah, we normally have
Oh,
in
but
in
the-
resets. Yeah, it doesn't now. You can have non-resettable flip-flops. That's fine. Those exist. The other important thing that you need for all of flip-flops is clock. So that's an important one.
Oh my gosh,
And you need to
yeah.
do that too.
I don't know
Every
why I
input,
assumed that
every
they
output.
did
We take it for granted. We're like, oh yeah, we have a clock, we got a reset. Just,
Yeah.
no, these are important ones. Okay. You'll notice that I put input logic on a different line than the first one. That's only because these are different bit widths than A. These are 1-bit signals. You don't actually have to put it on a new line. You just, if you were to put it on the same line, it would look like this. But I personally don't prefer it looking like that. I like them lined up. So that's why you'll see me typing like that. Okay, so I'm going to assume this is a resettable register.
Wait, so then
Yes.
you need to have clock in there though, right? Input logic clock.
Oh, you can't see it. Sorry.
Oh yeah. No, I can just see reset.
Let me...
Oh, there it is.
There we go. All right, sorry about that. So yeah, we have reset and clock in there. So now, in my always block, I'm going to basically type up how I want it to behave. So the way we want a flip-flop, a resettable flip-flop to behave is, if the reset signal is on, we just go to our reset state. So I'm going to type that up. So if reset is on, then the state that we're in is going to receive the value of SR, because that's our reset state. Now, I know I haven't defined a state anymore.
Yeah, I was just
I'll get to
wondering
that in a
how do we
second.
know what-
Yeah, no, that's a, yes. I will get to that in just a second. So, state here, that's literally the current state bits of my registers, the ones that appear on the left side in your schematics. So S2, S1, S0, that's what state is going to be. So I need to make an internal logic signal to represent that. It's not external because it's not feeding in or feeding out. So I'm going to go and do that up here. Oops. So here are going to be my internal signals. So I'm going to say logic. I don't say input. I don't say output because it's not an input or an output. It's internal. So I say logic. And then I'm going to put 2:0 because it needs to be a 3-bit state. And I'm going to say state. I'm also, since I'm here, going to have another signal for the next state, which is the wires that are on the right-hand side of the register in your schematic. Okay. Now, what I'm going to do next is, now that I have these internal signals defined, I can actually use them in my logic. So if reset is on, then my current state is going to go to SR. But otherwise, if that doesn't happen, what do I want state to be? What do I want the state to go to?
So if we're not on the reset,
If it hasn't reset, where is the state going to go?
oh, then it goes to the state.
Yeah, so I just say the next state. And that's why I defined next state up here.
Okay.
Oops. All right. Now, you can, if you want, put a begin and an end statement for any of your blocks. This is like the curly braces in C code, but in System Verilog it's begin and end. I will say though, You don't always need to put it. If there's a single line, a single statement, you don't need to specify. And if there's a single complex statement, I'll talk about what that means in a second. If there's a single complex statement, then you don't need to put it either. Here, I have an if followed by an else. That's considered one large complex statement. So actually, I don't need the end, and I don't need the begin. The parser for the code understands that all of that stuff that I have tabbed is supposed to be within the always block. And just so you know, the tabs don't matter. It's not like Python code. It doesn't matter how I tab these. That's just for formatting. All right. So now continuing on, what we've just done in our schematic, I'm going to draw out. So I think I might have said it backwards earlier. These are your next state bits. These are your current state bits. I think I might have said it backwards earlier. So that's why I'm re-specifying.
There on the left side.
This is what we've just made. So literally, our code is going to instantiate this register. And so now we need to do the last few components. So the first is going to be the next state combinational logic. So that's from your next state table. And then the last step is going to be the output logic. Any questions for me so far? We have no idea how the code is going to make our logic unless we specifically tell it to use particular gates. And at that point, the point of the code is kind of redundant because we would have had to go through all our tables to get gates versus using the thing in code where you can do like a case statement and say, if this, then do that, if this, then do that, etc. So I'm going to do a little bubble here because for the moment, we don't know what the logic is going to look like. And then here's more combinational logic. For our output signal, it's just a 2-bit signal.
Wait, what the hell? Listen, I received a message from Amazon.
And so this is the general format for pretty much any schematic, or any FSM. You're going to have your input combinational logic for your next state, you're going to have your output combinational logic, and then your state register here. So we'll go ahead and work on this part. Now, there are many ways you can do this. Like I mentioned earlier, one way is to, kind of the brute force way, is to write out the tables yourself, turn them into their Boolean equations, and then convert those Boolean equations into assignment statements. So just like we did as practice for some of the other system Verilog questions, you can say, for example, if next state bit 2, for example, if next state bit 2 was the equation A and B or C, you could literally write A and B or C, and then that would work. I don't want to go through the work of that. Most of the time, you can go straight from this, without, straight from the FSM diagram, straight to code. You won't have to. Yeah, so that's what we're going to do. So I'm going to make another block here. So up here, I made a sequential block. Sequential meaning there's a time component. Down here, I'm going to make a combinational block. And the way you do that in System Verilog is always underscore comb, where comb stands for combinational. And then within that always comb block, you can do a variety of things like if-else statements. But what I'm going to do is I'm going to do a case statement. And my case statement is going to depend on my current state. Because recall that our combinational logic here depends on two things, the current state and your input. So I'm going to have different cases depending on what state I'm in, and then all I'm going to have to do is say, if you're in state SR, so if the case is SR, Then I check, hey, is A0, is A1, is A2, is A3, and what do I do in each of those cases? So I'll go ahead and type that up. And as a small side note, the case statement is also regarded as one long complex statement, so I don't have to put a begin and an end. You could if you wanted to. There's no harm in it. It just kind of, you just type extra stuff in the code. Okay, so you'll notice that I've actually put 2 lines on my case statement. The reason why I've done that is because whenever you have any kind of case statement in your code, you want to put a default case. And the default case is basically just going to pick up on any other possibilities, including states which are not possible. So say the state 111, we haven't encoded that one at all. So that state's not possible, but just in case for some reason, like if radiation hits your wires and it flips one of the bits to 1, well, now your circuit can still handle it. Maybe all of your values on your wires are like 2.5 volts. Now your circuit can handle it, despite the fact it's not a nice logic 0 or 1. So in this default statement, I'm just, as the designer, I'm going to choose to set my next state always equal to SR, back to the reset, a known state. You can do whatever you want. You're the designer. It's up to you to figure out what you want to do in the default case.
Seems safe.
Seems reasonable.
Yeah.
Okay, now in the rest of these, I'm going to basically reference my diagram. So my diagram says that if I'm in the reset state, well, let's talk about the different transitions. If I'm in the reset state, I have a few options. I'll code up this one first. So if A, bit 1, the most significant bit of A, is true, and when I say is true, you might think to do like in C code to do something like this, but you can actually just leave it like that, just as the bit A. So if A is true, then what we're going to do is we're going to say next state is going to be the value SR, because we're staying in SR if A bit 1 is true. And so all I've done is I've taken that transition on my diagram and encoded it in my code. Now I'm going to do the next one. So the next one I'm going to do is I'll do that one, the transition to S1. So the transition to S1 says else if. Now I can type this one of 2 ways. I could say not A1 and A0, which is exactly what I've written up on the board for that transition. A1 bar and A0. However, because of the way that the compiler is going to read the code and kind of the way we think of it when we say it out loud, we first check if A is on. If A is on, this gets executed. Otherwise, and that otherwise means A is not on, otherwise we go to this line.
Oh,
But if we're
that's
at that line,
redundant.
we already
We
know
A is not
that
on.
A1 is not on.
Yeah.
So we could just write this, and that would be fine.
Is that good readability though?
That depends on the reader. So to me, this makes sense because
Oh.
I know
Yeah.
if I get to that else if statement, that means that A was off.
Yeah.
So I know that. If it's not readable to you, leave it the other way. So I don't care. I'll do it this way just to be exactly precise with what I mean, and also to relate to what I have written up on the board. So now, in this case, where did I transition to? So that transition took me where? That's right. Yeah. Yep. So that transition took me to S1. And now I'm going to finish it just with an else. The reason why I'm doing an else instead of an else if is for the same reason that I have a default. Just in case, for some reason, that doesn't cover all the cases. Say, logically, we've already covered all 4 possible cases, but if there's an undefined bit, like an X, then our else case is still going to catch up.
Oh yeah. Well, what about the 1 to S2?
That's what I'm doing here, yeah.
Oh, okay.
Yep. So
Oh,
otherwise,
I see.
we go to S2.
Okay. For some reason, like it would make sense in C++, but like this is for some reason
Yeah, I mean,
confusing me.
it's good that you're not trying to think about it in terms of C++ because there are some related things, lots of the nuance is very, very different. For example, this state register, it's not made before the next state logic. All of it is just circuitry on a chip. One thing does not come before another. They're put there simultaneously or in parallel. And so I could put this next state logic above the state register and it wouldn't matter. If I put this stuff up here and the state register below, makes no difference. It's the same hardware. The way I know the ordering is the interconnects of the wires that I specify. That's how I know how they're connected. But the actual order that I type them up doesn't matter. So I could very easily put my state register down below this. Makes no difference. It's all done in parallel, unlike standard code that you would find. And that's how it is for most hardware description languages. Okay, I'm going to go ahead and go through the rest of the states relatively quickly, and I'll just start to type them up. So I have state S1. So S1 only has one transition, and it's always taken. So all I'm going to do is I'm going to type next state equals S2, because I'm always going to go to S2. There's no need to put an F or anything. If I'm in state 2, I only have 2 possible transitions. Either I go to state 3 if A1 is on, or otherwise, if it's off, then I go back to S1. So I'm going to type that up too. If A1, then my next state is going to be S3. And otherwise, I'm just going to go back to state 1. I'm going to do the same thing for S3. So I'll go ahead and take a look at S3, and I'll say, okay, well, only if both bits are on am I going to go to S4. Now I'm going to introduce some new syntax to you guys. So I could, if I wanted to, actually, I don't know if this is new to you, because I can't remember if I introduced it yet. But if I wanted to write this expression, A1 and A0, this is one way I could type it. Literally A1 ampersand A0. However, if you have a multi-bit signal and you want to take all of the bits from that signal and AND them or them together, another way is you just write the signal and you put an ampersand before it. That's going to take every bit from that signal and run it into an AND gate, just like how I had typed out. So if it was a 3-bit signal, it would be a 3-input AND gate with A2, A1, A0, and there'd be one output. So I'm going to leave it like this. You can also do this for ORs, using the OR symbol, and exclusive ORs using the exclusive OR symbol, which is the little caret. So that is important to know for the sake of typing. Okay, so if A1 is true and A0 is true, then our next state, our next state is going to be, I believe, state 4. Yes. State 4. However, in every other case, and that's why I wrote else on the diagram, otherwise, my next state is always just going to be what? It's going to retain its state, stay in S3. And then finally, for S4, again, like I mentioned, this is an unconditional arrow. You always go down that arrow. So I just write next state. Yep, next state equals SR. And my code is done for the next state logic. So I wrote this in code terms, and it's going to make some sort of gate level description of it and put it here for me. I don't know how it's going to look, but I know that it's going to work. One minor nuance you can, or one minor thing you can do for this is you can look at S4 and realize that if I didn't write this line of code for S4, actually everything would still work.
Oh, because you have the default?
Because the default exactly covers that situation. So you could omit it if you wanted to, but for the sake of having everything there, I'm going to leave it. Okay. So we're almost done. We've done the hard part now. We did the state register first. Not too bad, a few lines of code. We did the next state logic. Also not too bad, a lot more lines of code, but it's just translating these arrows into code. And then the last step is we're going to get the combination logic for our outputs. So I'm going to put that down here in my output logic. Again, like I mentioned before, it doesn't matter what the order is that I put these. I could put the output logic at the top if I wanted to. It wouldn't make any difference. Now, for this output logic, I could, if I wanted to, do another always com block and have it depend on the state, and then just say, if you're in this state, then y equals this. If you're in that state, y equals that. I could do that. But because I've already done that for the next state logic, I'm going to instead do it with assign statements, so you have practice with those. So what I'm going to do is I'm going to say assign, and I'm going to split it up into the different bits. So I'm going to do y bit 1 in a separate assignment statement from y bit 0. You could do them together, and I can show you how to do that. But for the moment, it'll be easier to consider them separately. Okay, any questions so far? I know I've been blabbering on for about 45 minutes straight.
No, this is great.
Okay, so I'm going to take a look at my states on my diagram, and I'm going to figure out when the most significant bit of y is on. So it's not on in state the reset or S1, but it is on during 2 and 3, and off during 4. So these are the two states I want to keep in mind. State 2 and state 3 is when it's on. So here's what I'm going to do. Y bit 1 is going to be on when the current state we're in, and I think, yeah, that's right. Y bit 1 is going to be on if the current state we're in is the same as S2, or if the current state we're in is S3. And you'll notice that I've done the double equal signs, very similar to C or C++. That's the comparison operator, as opposed to the assignment operator, which is this guy here, the single equal sign. So now with that in mind, now that I've written this out, I do want you guys to know that you do have to do these parentheses for each. You can't omit them because of the order of operations. It'll actually read the OR first, and then it's going to try and OR S2 with state, and then it's all going to be gibberish. So make sure you put parentheses around these comparison operators first. And we're going to do the same thing for y bit 0. So why don't you guys go ahead and tell me what the states are that we're going to have this bit on for.
So first one is going to be SR.
Okay, SR. SR, it's off though.
Oh shoot, we're looking for ones. Yeah, sorry. S3.
S3
Yeah.
and S4. There you go. No worries. So S3 and S4. Okay, cool. Now, just as a comment, like I mentioned earlier, I could totally write this out as one line where I'm doing both bits simultaneously. And the way I would do that is with the concatenation operator. And so what I would do is I would concatenate this statement, which is meant for the first bit, and I would take that and concatenate it with this second statement, which is meant for the second bit, or the least significant bit. I'll scroll down in case you can't see that. But all I did was I just took this first one, put it up here, a comma, followed by the second one. If you prefer it that way, be my guest. If you prefer separating out the bits, that's fine too. Whatever looks cleaner or makes you understand better is best. Okay. And I don't remember. Yeah, you guys can see that. Well, let me make that a little smaller because it is hard to see. There we go. Okay, so any questions on that? It is fine to ask questions, by the way. Okay. So we just finished our design. We started with the state register, then we did the next state logic, and then we did the output logic. Like I mentioned before, it doesn't matter what order you type them in. It's all going to be put in as hardware and wired up the same regardless. I believe I covered all of the points I wanted to, and you're likely going to go into an example like this in class, or will have already talked about one, or you can look at lectures that she's posted online for references. But this will get you started, and it'll help you figure out how to do the code for the homework problem.
That's great. Yeah.
Okay, so any questions about the entire process? Because I know we went through quite a bit. Okay. So now that we've gone over that one, are there any other topics that we want to talk about for the last few minutes of office hours?
Yeah, just a quick question.
Yep.
Would we get something like this in the test? Like, I know, like, they don't want us to handwrite code, so maybe, like...
No, you would
I don't
totally
know.
get, like, it wouldn't be a lot, but you could definitely be asked to write code, handwrite code for your exam.
Okay.
What I will say is that typically, if Dr. Harris does, which she normally does, ask at least one question, is typically not a lot of handwriting. So maybe she'd ask you to write the port for a module, so just the top few lines where you're listing out the inputs and outputs. She might just ask for that. Or maybe she'd ask you to write the code to instantiate a resettable flip-flop, just those few lines of code. Or maybe if she's having a particularly bad day, she'll ask you to write the next state logic for, what's it called? For an FSM. I'd be very surprised, though, if she had you write that much. Generally speaking, it'll probably be less than 10 lines. Most likely less than 5 lines of code of actual handwriting.
Cool. This is super.
You're very welcome. Okay. Any other questions, comments, concerns, grievances? I don't know.
You wouldn't be able to compile that in VS Code, would you? Or would...
I don't think so.
You would need, like, Questa, right?
Yeah, you would need QuestaSim, or you guys. It's going to be called Model Sim for you guys. I don't. Is that what she calls it in class?
That's what we
in
used
lab?
in the lab.
Yeah,
was Model Sim.
yeah. It's the same thing. They just renamed it. Model Sim is the free version, whereas QuestaSim is the one you have to pay for. And then you could also compile it in Quartus. I don't know if you guys have used FPGAs yet in lab.
That we're doing that tomorrow.
Okay, well,
It's
you'll learn
Quartus.
a little bit about Quartus tomorrow, and you can compile code in there as well, and then actually synthesize it, and then place and route it on your FPGA, download it, send a bit stream, and then it'll actually do stuff, which is going to be fun. But that, yeah, those are the only 2 programs that you'll be learning how to use for actual compilation. You could use ActiveVHDL, which is similar to Model Sim. It was made by Aldec, which is a company here in town, or a company that has a building here in town. It's basically the same thing as Model Sim, just a different company's version of it. And depending on the FPGA that you're using, where it comes from, they have a different software for it. So, for example, Intel has Altera, which creates the DE2 boards that you guys have, and their software is Quartus, whereas there's another one, I think it's AMD who owns it, Xilinx, which uses the Vivado software. But, if you ever use a Xilinx board, you'll get into that. But yeah, those are the only ones. I don't think you're able to actually compile it in Visual Studio Code.
Okay, thank you.
Yeah, for sure. I'm trying to think of other things that are important. Well, like I mentioned at the beginning, in class you will likely have seen or will see a different way to do the parameters. You do it with enumeration, kind of like in C code, where it's almost the same thing. It does the same thing as what I've typed up here. It's where you have a bunch of names and you assign bit values to those names. It's just a different way of doing it, using enumeration instead of parameters. Shoot, if no one has any questions, I can just go on for another 6 minutes. I don't mind. Because I know you guys haven't... Have you gone over parameterized modules in class yet? Okay. So let's say that you wanted to make a multiplexer. And you wanted to make a multiplexer module in System Verilog. The diagram I have drawn up here assumes that A, B, S, and Y are all 1-bit values. But the general process of how a multiplexer is created in hardware is the same regardless of how many bits there are. If A and B were 4-bit values, and you're selecting between either outputting B or outputting A, it's going to behave very similarly. And in that case, we often use what are called parameterized modules, so that at compile time, before we actually place stuff on the FPGA, we can customize what the bit width is, for example. That's an example of a parameter. So the way you do parameters in modules looks like this. So like I mentioned before, you type it right before the port list, and it's going to be a £sign followed by a set of parentheses, and in those parentheses I'm going to list all my parameters. So I could have multiple. I'm going to do 2 for the moment. Parameter width, parameter what's another good parameter? I don't know. Clock. This is just an example. And you can set default values for these parameters by setting them equal to a number. If you don't put a default, that's fine, but when you instantiate this module in another one, you have to specify those values. If there are defaults put in, you don't have to specify values. Now, the way that you would typically use these parameters is, and it's not always like this, this is just a typical case, is like I mentioned for bit widths, if you want to have configurable bit widths without making multiple modules just to change bit widths. So here I have a bit width of A of 1 to 0. Instead what I can do is I can write width here, so that I can have any bit width of A and any bit width of Y. However, just keep in mind, I'm going to have to put width -1, and the reason why is because if I want a bit width of 2, I would say 1:0. However, if I just typed width here, that would be 2:0, so I subtract 1 from it. Parameters aren't just used for bit widths, but that's like a very common use case. That's why I'm going over it here. And in your code, you would just have to be careful to make sure stuff is generalizable to multiple bits. So for example, down here, I have y bit 0, y bit 1. That wouldn't cut it, because what if it was just a 1-bit signal? Now where's this going? What if it was a 4-bit signal? Well, where's y2 and y3? So you have to be careful when you parameterize stuff. You have to make sure you know how you're doing it properly. I am not bringing this up to make you do a parameterized module now. I'm bringing this up so that later when you see them, you kind of have an idea of what they do. It's just to make it so we don't have to write multiple modules that all do basically the same thing with one tiny little difference. That's the only reason we use them. Yeah, I think that's about all I got.
Thank you so much.
Yeah, you're very welcome. Any other questions for me?
No, that's great. Thank you.
Yeah, of course. You have a good rest of your day.
You as well. Thank you.
Awesome.
It is chilly, huh?
Yeah, it's time to. I wish it was 100 degrees out.